Okay guys, today we're going to be looking at scientific notation and standard form as well as our exponent laws that you've probably reviewed in past math classes, but we're going to take a look, make sure we've got them all down before we kind of get into the nitty and gritty of IB math. So for scientific notation, the one thing we want to also make a note of, this is also called standard form. Of a number. Okay, and it's a kind of an easier way to write out very large or very small numbers when we go and do our measuring and things like that. So they're a number where A falls in between 1 and 10, okay, and then K is an integer, so this symbol represents our integers. So that's a positive or negative whole number. So K can only ever be a whole number, and then A can be a decimal, but the very first value should always be a single digit number between 1 and 10. So for example, if we take a look at 2,345 and I want to convert that into a standard form number, okay, I'm going to look at where my decimal is, and my goal is essentially to move that decimal so that there's only one number in front of the decimal. So in this case, it would be 2.345, which I then multiply by 10. And my number up here for my K is really how many times did I move that decimal. So I moved it 1, 2, 3 times. Okay, and you can double check, because if I take 2.345 and multiply that by 10 to the third, 10 to the third is really 1,000. Well, 2.345 times 1,000 would give me 2,345. I can go in the opposite direction too. So if I move my decimal 1, 2, 3, 4, 5, I'm going to get 6.25 times 10. Okay, but my number is technically supposed to be smaller. 0.0000625 is smaller than 6.25, okay? Which means if I'm going to be multiplying by 10, I really need to be dividing by 10, and I can represent that with a negative exponent, which we'll see kind of in our exponent laws off to the right side. Okay, and I moved my decimal 1, 2, 3, 4, 5 times, so that's 10 to the negative 5. Okay. And then from there, if we really wanted to, we could round with significant figures. So for example, our first one here that I'm circling in green isn't rounded to 3 sig figs. If I wanted to round that to 3 sig figs, I could do 2.35 times 10 to the third, which would be 3 significant figures. So if this were like an IB exam question, I could round that to 3 significant figures as well. For our exponent laws, okay, we're going to refresh ourselves a little bit on them. When I multiply two bases with exponents together, I add my exponents. Okay. When I have a negative exponent, that's really the same as dividing by that base to that power. So I can flip that over a fraction bar and make that exponent positive. That's why I was saying with our standard form, that negative exponent really makes the number smaller, because in reality, I'm dividing 6.25 by 10 to the 5, rather than multiplying by 10 to the 5. For when we take a power to a power, right, so x to the n to the m, I multiply my exponents together. So I'm going to go x n times n. Okay. When I divide the same bases, I subtract their exponents, x to the n minus m. When I raise two different bases to a power, both base get that power, so I get x to the n, y to the n. Same thing works if it were fractional, okay? So if they were x divided by y, both variables would get the power. And then anything to the 0 power is 1, okay? If you're writing something down, feel free to take a second, pause the video, but I'm going to go ahead and move on to some simplifying exponent examples on the next slide. Okay, so if I want to simplify this first expression here, there's a couple of different ways you can do it. I recommend always dealing with powers to powers and negative exponents first. So I'm going to start off, I'm going to keep that x cubed and y to the fifth the same for a second. And I'm going to go ahead and distribute that -2 to both things that are in my parentheses. And when I take a power to a power, I multiply the exponents. So I'm going to get x -2 times -2 gives me +4. And then 3 times -2 on that y gives me -6. Okay. And then I'm going to go ahead and deal with that negative exponent. So next step, I'm going to still keep my x cubed, y to the fifth, times, I'm going to flip that y into the denominator. Technically, x cubed y to the fifth is all over 1, so when I go and multiply these fractions together, what I'll end up with, I'm going to move down to the next line here, okay, is I'm going to get x cubed times y to the fifth times x to the fourth all over y to the sixth. I can simplify that numerator. So x, when I multiply something of the same base, I add their exponents. So 3 plus 4 gives me 7. Y to the fifth over y to the sixth. And when I divide the same bases, I subtract their exponents. Note that the bigger exponent is here in the denominator, the 6, which means any leftover y's should remain in the denominator since there's more there than there are in the numerator. So I'm going to get x to the 7 over 6 minus 5 gives me 1 y left over. And there would be my final simplified expression. There's no other, I don't have repeated variables anywhere, there's no parentheses, and we typically try to avoid leaving negative exponents in our answer as well. For the second one, like I said before, I typically prefer to deal with negative exponents and powers to powers first. So I'm going to change colors here. I'm going to leave x to the fifth over y to the seventh the same, times, I'm going to go ahead and distribute that -1, so x to the -2 over y to the -3. All right. I'm going to deal with my negative exponents. So since they're both negative, I can just flip the x to the -2, y to the -3, make those exponents positive. I'm going to keep x to the fifth over y to the seventh the same for now. So y cubed over x squared. I can multiply across for fractions. So that's going to give me x to the fifth, y cubed, x to the second, y to the seventh. And now when I'm dividing things of the same base, I subtract their exponents. Okay, x to the fifth is the bigger power there. So x to the fifth, I'm going to subtract 2 for the x squared in the denominator. So that's going to leave me with x cubed on top. 7 is the bigger exponent on the y's, which means when I subtract, I should leave my y's in the denominator. So 7 minus 3 is going to leave me with y to the 4th. Okay, and again, no parentheses, no negative exponents, and I only have one of each individual base. So everything is as simplified as I can really get it. I'm going to switch back to red for the bottom problem. Okay, so this time we could type this directly into our GDC, since for IB Math AI, you will always have your GDC, and you can get an answer. We can also apply our exponent rules here to these scientific numbers, or these standard form numbers. Okay. So what I'm going to do, I'm going to focus on the left side first. 3.0 divided by 1.5, that really gives me 2. And I'm going to go ahead and put a 0.0 there, since we know with standard form numbers we typically have the decimal there. times, okay, and I can actually put that over 1 so we can kind of keep our fraction as well for now. 10 to the 4 over 10 to the negative 2. So I'm going to go ahead and flip that negative 2 up. So that's going to give me 10 to the 4 times 10 to the 2. Okay. All of that over 1. I don't have anything left in my denominator anymore. Okay. Everything either flipped up or 3.0 over 1.5 canceled and became 2. Okay. Well, when I multiply something of the same base, I add their exponents. 10 is the same base, so I'm going to get 2.0 times 10 to the 6th. And that would be my final answer on this one. Okay. Now, if you type it into your calculator, you might want to be careful because it could just spit out the whole number answer not in standard form. And the IB exam question might be specifically expecting you, if it says it in the problem, to leave your answer as standard form. Okay. But here, that would be my final answer. Okay? If you have any questions, again, feel free to ask in class. I'm more than happy to answer any questions that you got. Otherwise, thank you all for watching.